Okay, good afternoon. Let's start lecture. Just a few words before we start the lecture. The final exam is December 3rd. So practically before the final exam, we only have, including today, only have 5 lectures to go. Okay. And as I always say, basically, as you probably will find out, the last few lectures, particularly the last 2 or 3 lectures, is the highlight of this course. Highlight basically means you're basically making use of everything that you learned since the beginning of the course for the last 2 or 3 lectures. So that's how important the last 2 lectures, basically last week. And I'll practically cover until the end of the term. So you shouldn't, lower your guard. Oh, here's the last lecture, probably just a review or something, right? So actually, often in time, not often, as always, there will be a couple of questions from the last 2 lectures. Question, right? Yeah. Surface integral, Stokes theorem, divergence theorem. Yeah, those words you will learn in the next few lectures. Those are really important. Okay? Yeah. So just a heads up in terms of that. Okay. And also from here, you will see is the calculation a lot of time when I give it to you is not that bad. And what you right now, what I want you to bear in mind is trying to understand what's behind the formula that I'll give you today is more important. Okay? Yeah. So we're going to start a new topic called conservative field, but before we go that, let's do a quick review from the last lecture, which is a bit of already more than a week ago, the vector line integral. Okay. So everything we're doing so far until the end is integrations within vector fields. Okay, integration within vector fields. So vector fields essentially we have a let's see, we have a vector field F. Okay, so F, suppose that is M, N, P. Okay, there's 3 components, M, N, P, and each component is probably a function of x, y, z. Okay. So if you plug in a certain point x, y, z in the 3D space, you will be able to basically plot, sketch a certain kind of a vector field. Right? That's a vector field. So the first type of application is let's look at vector line integral. If I have a curve, okay, say, okay, r of t, okay, so the r of t is within this vector field. So now if I'm going to move from this A to B, okay, yeah, so then we used a concept, let's say the vector field is a force field. So how much work this force field will do, or the total amount of work the force field will do if to move a certain object from A to B, right? And in that derivation, what we did is, so for a small amount of work, okay, to move from here to here for a very small segment at here. And what we do is, okay, we draw a tangent lines, okay, very small tangent, we call it ds vector. Okay, so basically, ds vector represents this one here. This is what we call a differential displacement. Okay, differential displacement. So it's a little bit different from the previous lecture. In previous lecture, you usually say, okay, there's a differential arc length ds. Right now, we're considering there is a vector concept here. Okay, this is a direction. So this is a differential displacement. In other words, it has a direction, it has a magnitude, right? So the ds has a direction, has a magnitude. And the direction is basically the t hat is the tangent vector, okay, the unit tangent vector. Okay. And the magnitude is ds is the arc length, as we learned before the midterm for the scalar line integral. Okay, so this small segment at here, okay, this small segment, that's the ds, right? That's the scalar quantity. And then you have the t hat, so together you have the ds vector. Okay, yeah. So the amount of work that you do, the amount of work this force field will do is F dot ds. Okay, that's the small amount of work, differential amount of work that this force field do to move from here to here. Okay. Then the total amount of work is basically W equal, okay, integrate along the curve C, so F ds. Right, so integration, basically W equal to integration of dW. Okay, yeah. So that's a line integral, right? That's line integral. So from here, there are slightly different, okay, appearance for this line integral when you try to evaluate it. Okay, so first of all, now we understand what F is, the force field, and ds is the differential displacement. Now, what is the differential displacement? Basically, this is a vector, and this is basically dx, dy, and dz. Okay, that's the differential displacement. So you move in certain direction, dx, dy, dz, right? That's a little bit displacement. Okay, then in terms of calculation, okay, we know that, okay, as we did, we can write, you can see now we have a different kind of formula now. So what is ds? ds is a t hat, okay, times ds, right? So vector has a magnitude and direction. Okay, so that's ds. And we're integrating over this curve C here. And the curve C, suppose that we know that, is this represented by a parametric equation R of t. Okay? Yeah. So t hat is basically the unit tangent vector for this curve C. Okay? So t hat is dr over dt over its magnitude. Okay? And ds is the arc length, as we derived in the previous lecture. It's dr over dt dot dr over dt times dt. Okay, times dt. So then if you plug a t hat here and a ds over here, okay, we end up with a slightly different formula now, right? So just remember you have a different. This is 1, 2, right? This is 1, this is 2. They're all the same thing, okay? Line integral. Now, but once you plug t hat and ds over here, you'll get a slightly different, expression. So this time you got dr over dt and dt. Okay, so you get this. So the last one, so this is number 3. Then if I plug in this, cancel this dt out, okay? I got this one here, right? So now you see 1, 2, 3, they all same thing basically, okay? They all refer to the same line integral. Just remember the difference between the symbols here, right? The R here is the parametric equation for the curve, okay? And ds is the differential displacement, okay? Yeah. And as a matter of fact, and you can actually have one more formula for this line integral, because remember what we said is suppose the vector field is f equal to m in p. So vector field is m in p, and the line integral r of t, maybe it's certain kind of a vector function, a parametric equation. Okay, maybe it's x of t, y of t, z of t there. All right? Yeah. So from here, you see, I can actually plug in this m, n, p dot, right? This dr that differential. This is differential operator. Differential operator r vector. So what does that mean? Differential operator. So basically d here. When you put a d, it's dx, dy, dz, right? Yeah. So this is dx of t here, and dy of t here, and sorry, not a vector, and dz of t here. Okay? Yeah. So this is a dot product. Then technically what you do, you basically apply the dot product formula. So you got m dx here plus n dy plus p and dz. Okay? Yeah, there. So now this is number 5. So you basically, for the line integral, you can have 5 different kind of formulas, okay, to calculate the value of the line integral. Okay? Now generally, the most used one is probably this one here, to number 3. Okay? Yeah. Okay, so just bear in mind of the differences, the symbol, that's more important. Understand each one of the symbol here. Okay? So let me give you an example, and then we'll move on from this line integral. And of course, I think as you do assignments, you will if you recall that when you do scalar line integral, basically similar stuff here. For this vector function f right here, this vector function f, before you start to integrate, because the original f vector function, this is in terms of x, y, z. So you're going to have to replace whatever this x, y, z right here with the parametric equation from this curve C. Okay, that step is very important. You have to do that before you are able to evaluate this line integral. Okay. So let's see this example here. But sometimes we have some shortcuts, okay, to do this line integral. So I have a vector function f equal to x I hat plus y j hat, and the curve C is a square, okay, with the radius of a. Okay. Now, what we want is we want to calculate the line integral, okay, for this vector field f, okay, over this curve C. Okay. So, if I draw the curve C out here, here's a circle, okay, and there's a radius of a out here. Okay, so we want to integrate this line integral over curve C. Okay. And the vector function or vector field is x, y. So basically, if you plot it out, it's pointing out, right? Basically, it's as it going outward, the magnitude of the vector will start to increase. Okay, so it's like that kind of vector field. So now the typical procedure, what you do is you see if I need to apply any one of this formula here, I need to know the parametric equation for this curve C here, right? Parametric equation. So this is a curve. This is a circle, so it's pretty straightforward. And for this parametric equation, it's what? It's a cosine t and b and sine t. Okay, I hat plus j hat. Okay, so that's parametric equation for the curve C. Okay. And then if I apply formula, then what do? This vector function f, right, which is this. So basically, you have to replace this x, this y, with x of t and y of t. So the vector function f will become f equal to a cosine t and b sine t, right? Yeah, yeah. Oh, sorry. Why do I have where's the b from? Yeah, it's a here, right? Yeah. Okay, very good. Okay, so this is f. It will be replaced with a cosine t and a sine t because the x and y are here. And the dr, right? This is basically where you will apply the formula now. You'll see, okay, maybe maybe I don't use number 4. I use number 3, right? Yeah, because ultimately what you're integrating with is respect to the t, right? So basically everything has to be transformed into the variable t. And this has dt naturally showing up here. So all I need is a dr over dt, right? Yeah. So I guess I'll just calculate dr over dt out here. Okay. So dr over dt is pretty easy. So it's negative a sine t, and then a cosine t. Okay, yeah. So that's it. That's basically the time for you to plug in to do the integrations now. So say this vector, so this vector here. Dot that vector, right, and dt. Okay, dt. That makes sense? Yeah. So the integral limits is the limits for the t. So this is a circle, full circle. So the t goes from 0 to 2 pi, right? 0 to 2 pi. And as you can see, if you look at this one here, what does it give it to you? 0, right? You get a 0 here, okay? Because the dot product gives you 0 basically, okay? Yeah. Oh, okay. So now this is basically the next thing I want to point out here. You do have a shortcut. So let's say I'm going to actually try to use this one here, okay? Try to use number 2 formula. Okay, number 2. Look at this one here. Number 2 formula is the f dot t hat. Remember what t hat is? T hat is what? Is the unit tangent vector of the curve, right? Of the curve. So for this particular case, what is if I locate point at here, and where is that f vector? What is the vector field from here? Because as I join it out, it points outwards, right? And if you extend that, that's gonna basically join this origin there. That makes sense? That's vector field. And what is the t hat direction? T hat is tangent vector to the circle basically. So t hat got to be this way, and f got to be this way. So it doesn't matter where you pick the point, the f and the t hat is always perpendicular. So basically, if I apply this formula here, just this dot product will guarantee to give you a 0, right? So you don't really need to calculate any derivatives or parameterize the curve. That makes sense, right? Yeah. So this is basically the idea here. Okay. So sometimes it could save you some time if this kind of special case come into the picture. Okay. So that actually tell us a phenomena basically. So this thing at here, this all the 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. Those are, remember what I call it? I call it basically, if in fluid mechanics, I call it circulation, right? Circulation along curve C. Okay, it's a circulation along curve C. So circulation along curve C. So which means this is circulation of F here, okay? Of F along curve C. If the F is perpendicular to the tangent vector, unit tangent vector of the curve C, then that means what? There is no circulation, right? But if the F is in the same direction as the tangent vector C, then you actually would expect to have the so-called maximum circulation along the curve C. That makes sense? Right? Yeah. So we're going to make use of this concept, okay? Pretty short between me today or next lecture, we'll talk about the curl concept. Okay? Yeah. Okay. So any questions on the line integral here? So good? Yeah. So now let's start a new topic, okay? The new topic here is conservative field. Okay, conservative field. Okay. So let me write down the line integral. Okay. Just one of the formula for line integral. Let me write down here. So now let's look at this formula. So this formula, if you recall that, where's that? How's that formula derived? Basically, you had a dw at here, and then equal basically a w equal to integral of a small amount of work, right, and equal to this one, right, and equal to this. Okay. So now if I compare, let's see now, if I compare these two integrals, okay, if I compare the two integrals. Because the two integrals are the same thing, right? Equal. So if I compare the two integrals here, what does that mean? That means what? That means this, as we derive this dw equal to this quantity, right? So that's something we have worked with. So that's okay, right? So dw equal to this. Okay. So now let's move from here a little bit here. Okay. ds, as I said, is a differential displacement. So what is ds? So ds is a differential displacement. So dx, dy, dz, the vector. And f is the vector field, right? Is a vector field. Suppose it is given, so it has three components, m, n, p. Okay, so m, n, p. Okay, so dw equal to f dot this. So what does that equal to? So expand it out, equal to m dx plus n dy plus p dz. Okay. Is that okay, right? Yeah. Okay. Now let's look at what is the dw, right? dw. W is the results of this integral here. Okay, is the results of the integral. So let's suppose the w is a function of x, y, z. Okay. Suppose that w is a function of x, y, z. So what is dw? We learned in the multivariable calculus. dw is called what? Total differential, right? Total differential. So if dw is total differential, and the w is the function here, is the function x, y, z. So how do I write this total differential? It's a partial w over partial x dx, partial w over partial y dy, and partial w over partial z dz, right? Yeah. So that we end up with this basically here, right? End up with this. Okay? Yeah. Or this whole left side here, you know, basically you can write it as what? Basically, it is a partial w over partial x, partial w over partial y, and partial w over partial z dot dx, dy, dz. That makes sense, right? Yeah. So now I want you to compare this one with this one. Okay? Compare these two. So what's the common one? Common one is this is a common one here, right? This is the common. And this side equal to this side here. So what does that mean? That means this vector has to equal to this vector here, right? And what's this vector? This is a vector field F. And what about this one here? Partial W, partial WX, partial WY, partial WZ. What is this vector here? What do we call this? Gradient. This is the gradient, right? Del W here. So you basically got, by doing these steps here, you got this. F equal to del W. Okay? You got F equal to del W. So now let's move back to this line integral just here. This is where we started, and this is where we ended here, right? Yeah. So sometimes this is called an integral form, and this is called a differential form. Okay? Yeah. Particularly when you learn electromagnetics, you know, Maxwell equation, there's over two different. One is in the differential form, and the other is in the integral form. But anyhow, now what I end up with this guy here, right? Now let me use probably a physical meaning in here. So we use F. We consider F as a force field. Okay, as a force field. Let's say F is not a force. F is a gravitational field. Okay, it's a gravitational field. So you have this gravitational. This is gravitational field. And then you're moving, okay, a certain mass from A to B, move from here to here. So what happened after you move from A to B? And this is what you're doing here, right? You do the amount of work. But in turn from A to B, basically the difference between A to B is what we call the potential energy, right? So when you move it up, this W at here basically represents is a potential energy change. That makes sense, right? So this W at here, if F is a gravitational field, and this is a potential energy, right? The potential energy, the W. Okay? Yeah, go ahead.
With the vector field F equals del W, go down a little bit.
Yeah.
Is it still F ds, or what happens to ds value?
We're comparing these two sides here, right?
Right.
So basically, this is the same thing. So that basically end up with this vector has to be the same as this vector.
Right.
And that gives us, and this vector is f, and this vector is the grading vector. So that's where I'm getting this one here. So the ds is gone. Is that your confusing it here? No?
Well, yeah, where did it go?
Where did it go? Oh, I don't need it anymore, basically, right? What I need is this one here. I need from here, right? So this side, these two boxes here. From these two boxes equal to each other, I derived this F equal to del W. Okay? Yeah. Now, this is basically a pure mathematical concept now. If I get rid of this, whatever field it is, and essentially, you can always create, you can always create a vector field using a scalar function. Does that make sense? You can always create a vector field using a scalar function. How? By apply this gradient operation. So basically, this one here is, we can call that a gradient field. Okay? It's a gradient field. Okay? So let's say you are using a hose to spray your garden. Okay? And the water coming out of the hose is a scalar function. However, when you consider it's the flow, the velocity, so the scalar function created a vector field. How did that happen? Gradient operation. Okay? Yeah. And if you look at certain whirlpools or kind of phenomena, basically, and there's a vector field created because of a certain point flow of fluid, right? Yeah. So the point flow of fluid described by scalar function can create a vector field. And what we learn next is a vector field can create another vector field. That's what we're going to learn next. This is a curl. Okay? Yeah. So this F is a gradient field. So in general, this small function f at here, okay, is called a potential function. Okay, it's called a potential function. So if you just apply the gradient operation to a scalar function f, you got a vector function, right, or vector field, and that f mathematically is called potential function. If you're in a Earth's gravitational field, so you can call the F as a potential energy, that kind of idea. All right? Yeah. And similarly, if you're dealing with electrical field, okay, if you're dealing with electrical field, let's say in electrical field, okay, so we generally use a E to represent the electric field, and the E equal to, okay, this guy here, and this one here is called electric potential. Okay, it's called electric potential. So you apply the gradient operation to the electric potential, you get this E at here. Okay, you get this electric field. And I have an example in the lecture notes. I probably won't go over it now, but you can try this. Electrical potential, okay, is equal to this for point charge. Okay, is this. Okay, is this. So Q is a point charge, and epsilon naught is this electrical, vacuum permittivity or electrical constant. Okay, so you have a electrical charge, okay, placed at origin and here. Then the electrical potential is this function. Okay, so R is from origin to anywhere in the 3D space. Then what is the electric field caused by this point charge Q? And you can apply this formula, negative del phi E, okay, to calculate this E. So there's really nothing strange mystery here. The R is basically the distance from here to here. So R equal x squared plus y squared plus z squared. Okay, yeah. So plug it into here, calculate 3 partial derivatives, you'll be able to find out the electric field. And of course, you probably learned in your first year course, the electric field is this, right? It's a Q over 4 pi epsilon 1 over r squared and r hat. Okay, that's electric field. And similarly, you can also try the same for gravitational field. Okay? Yeah. So probably will write it here. If we have is a gravitational field, okay, a gravitational field. So gravitational field, the potential function or the gravitational potential is this. Is V equal to negative Gm over R. Okay, Gm over R. So M is the mass of Earth, and G is the gravitational constant. Okay. Then the gravitational field, we use this small g vector to represent the gravitational field. Then this G, okay, equal negative del V. So del potential function, and you can easily obtain this one equal to, okay, this. Okay, that's gravitational field, right? Yeah. So apparently, the value of the G is different at a different height, altitude, right? Yeah. So one of the U.S. satellite, what it recently does is it maps out this the magnitude of the gravitational field around the whole Earth. So it actually revealed the some secrecy for underneath, the geology of the mountains under the sea, right? Because in the past we cannot see below the waters. So based on this gravitational field, right, now we're able to look at what it looks like, under the water. So anyway, what's the fuss of talking about this F del F right here, right? Yeah. The point is, if we have a vector field F equal to del F, that's a special vector field that we call a gradient field. And now, if we're going to do a line integral within this vector field F, and we have a very unique and useful theorem or shortcut to reduce our amount of computation. Okay? Yeah, so this is basically the next point here. if f is this, or basically f comes from, okay, del f, right? Yeah. So by apply the gradient operator to the scalar function f, you got a vector field f. So if this vector field comes from there, then we have this so-called, okay, we have this so-called very important theorem called fundamental theorem of calculus. Fundamental theory of calculus, have you heard of this, right? That's the first year. But this time it's for line integral. Okay? Yeah. So fundamental theorem of calculus for line integral. So what is the fundamental theorem? Let's write it down here, okay? Yeah. Given a curve C, okay, runs from a P0 point to P1 point. Okay. So basically, here's P0, here's P1. Okay, yeah, and probably the T will equal to A at the P0 point, and T will equal to B at the P1 point. And this is the curve, the parametric equation for this curve C, right? Yeah. And this F, okay, equal del F. So there is a vector field, okay, at here. And that vector field is a gradient field. It comes from a scalar function f, okay, by apply this del operation. Then the line integral, okay, as we have learned, there are different appearance for the formula. You don't need to evaluate this line integral anymore. All you need to do is this. Because this f comes from a scalar function f, right? So this is what the assumption is. So I'm going to replace the vector field f with del f, okay, dot dr. Okay. So, but we don't need to evaluate this. All we need is we need to do just do this. Okay, we just do this. So what does that remind you actually? So if this is a scalar function here, then a to b and equal what? F of does that look similar, right? Yeah. And this is called, what is this called? This is the fundamental theorem of calculus, right? We learned in the first year. And now we have fundamental theorem of calculus for line integral. Okay? It's very useful ones. And every year I will test this in the final. But I don't tell you that you got to use this. You only use this when you can't find the answer. Is that clear enough? Yeah. No, right? So, yeah, this is why you got to come to the lecture. So when you can evaluate the line integral, and you see there's no way you spend 3 hours, you can't even get the answer. And that means you have to think of some other options, which is this one here. All right? Yeah. So let me prove this fundamental theorem here, okay? Yeah, it's a pretty short proof, so I think it's good to have it. Let's see the vector, the parametric equation for the curve C, okay, arbitrary in general, generic ones. Let's see, it's x of t, z of t, and y of t, z of t. And the t goes from A to B, okay, as we plotted here. So t goes from A to B, okay? Yeah. And what are we evaluating? We're trying to evaluate this line integrals, right? Yeah. So let's plug it into here. Okay. This is where we are trying to evaluate. Okay. Yeah. The vector field f comes from a scalar function small f at here. Okay? So now I'm going to plug in the parametric equations and everything into here. Okay? Yeah. So f is certain kind of scalar function, right? Yeah, scalar function. So the integration is for t. So t goes from A to B, and del f. So del f is basically calculate the gradient vector of f. So what was that? It's partial f over x, partial f over y, and partial f over z, right? That's the gradient vector, okay? And dr, this is basically just like, as we said, this is basically dr over dt and times dt, okay? Yeah. So dr over dt, this is r right here. So dr over dt, you get dx over dt, dy over dt, and dz over dt, and times dt, okay? Yeah. Okay, so let's carry out this integral. Okay. So dot product, so multiply them together. So what do we get? We get fx dx over dt plus fy dy over dt plus fz dz over dt and times dt. Okay. Okay. So then, when you look at this thing inside a bracket here, and what does that give you? Well, actually, maybe you can do this first. Multiply the dt into the bracket. Okay? Multiply it into the bracket here. So what do we get? Okay? It's a total differential, right? Which is what? A to B df. Okay? A to B df. So what does the integral of df give you? Hey, give you f. And now you have this limits a to b. So this is basically proof f at the t equal to a minus f at the t equal to b, right? So when t equal to a, where is the location? This is t equal to b, t equal to b here. And this is a here. So when t equal to b, where's the location? Location is P1 point. When t equal to a, P0 point. So this is why the proof at here. Does that make sense? Yeah. So if you have the function f is a function of x, y, z, then all you need to do is plug in the coordinates of the P1. You get the scalar value. Subtract the same operation by substituting the coordinates of P0 over here. You get another value. So the difference is the line integral. Okay? Yeah. So this actually basically give us a a pretty good, I'll summarize it in more details next. If F, vector field F, okay, comes from the gradient operation of scalar function F, and you have this fundamental theorem of calculus. So now, guess what? If I same starting and same ending point P naught P1, but I'm going to choose a different, okay, different route or different curve R of t from here to here. Would there be any difference? So that actually is what we call what? Path independence. So just like gravitational field, right? So where, see the gravitational field, where does the gravitational field from? It comes from a scalar function by apply the del operation. So this gravitational field satisfies this condition. So in gravitational field, when you move from A to B, it doesn't matter how you move. No, right? Yeah. You do the same amount of work, basically. Okay? That's called path independence. So as a matter of fact, and as I'm going to summarize, this vector field F, as long as this vector field F comes from the scalar function F by doing this del operation, we call that conservative field. Okay, so might as well write it here. So F, okay, if F equal to this, and this vector field F is called conservative field. Okay? Yeah. So I'll talk about this a little bit in more details here. Okay, but let's look at an example of applying this fundamental theorem of calculus. Okay. So let's look at an example. So let's see, I have a vector field. Okay, and this is my vector field. Okay. I think I'll bring the pictures into the. So this is basically what we're going to do. This is the vector field. The red arrows is the field, and then there is a pizza inside this field. Okay, and we're going to integrate, okay, along these boundaries of the pizza. Okay, yeah. So basically, the curve C is C1 plus C2 plus C3. Now, what are each one of them basically? If you see that this AB is a straight line for C1, and DA is a straight line for C3, and C2 is a portion of a circle, right? And A is at the location of origin, right? A is the location of origin. And the circle, if you look at the length of AB, basically it's a unit circle, right? It's a unit circle here. All right? Yeah. What's the D's value? This is 45 degree. Okay, it's 45 degree. Okay. So, given this numbers, I guess if you're going to calculate basically line integral, guess what? Say this is the line integral you're required to calculate. Then technically what you need to do is C1, C2, and C3, right? So 3 segment piecewise to calculate line integral. And mathematically what I need is I need the parametric equation for AB, C1. I need parametric equation for C2. I need parametric equation for C3. And so this is this week's of tutorial that you're gonna make. You'll see that that's how that part of the calculation is done. Okay? Yeah. So calculate basically the conventional approach of calculating the line integral. But now in this question here, okay, well, I'll show you how, but this vector field actually comes from a del F operation. If this F is equal to xy, okay, if you let this scalar function f equal to xy, then the gradient vector del F give you this y and x here. Right? See, the first one is partial f over partial x, partial f over partial y, right? So that gives you yx. So what does that mean? That means this vector field capital F is a special one. Okay? It's a special one. So we had to treat it specially. So which means when I calculate this line integral here, I actually can skip away from certain computations by making use of this fundamental theorem of calculus for line integral. Okay? Yeah. So let's see. If I apply C1, what is the fundamental theorem of calculus? It tells me I just need to calculate what? The value of the scalar function f at the beginning minus at the end minus the value of the scalar function f at the beginning, right? So for this particular one here, if I apply the fundamental theorem calculus for line integral, it actually should be what? F of b minus f of a. Okay? Yeah. So what is the coordinates for b? It's 1, 0, and a 0, 0. So and f is equal to xy. So you probably should have a question here. How do you know f is x and y by the given vector field this, right? Yeah. So that's what we're going to deal with next, okay? So given vector field f, how do we find the scalar function f? Or maybe the question is whether there exists a scalar function f or not, such that del f give us this function, vector field f, okay? Yeah. So anyway, so the f function is xy. So now all I need to do is what? For the f of b, so what's f of b value? X over here, 0 over here, so it's 0 minus 0, which is 0. Okay? Yeah. The second portion, second part of the curve is f of c minus f of b. Okay? F of c minus f of b. So what is the coordinate of c then? Oh, sorry, this is d. Use the d here. So what's the coordinates for the location D? This is 1. This is 45 degrees. So the coordinate of D is so this portion is x and this portion is y, right? Now which is what? So this is 1 and here. So 1 times cosine 45 give you x, and 1 times sine 45 give you y. And cosine 45 equal to sine 45 degree, which is root 2 over root 2, root 2 over 2, right? Okay? Yeah. So that's the c coordinate. Okay. So then f of sorry, not a c coordinate, it's a d coordinate. The coordinate is d, right? So the coordinate of d is root 2 over 2, root 2 over 2. Now I need to plug this root, plug it into this function f. This is f of d. Okay? Yeah. So what does that give us? This times this, 2, 1 half, minus 0, 1 half. Okay? Yeah. Yeah, any questions? All good, right? So last portion, C3. is f of a minus f of d. Okay, so f of a is 0, f of d is 1/2, so it's negative 1/2, right? Negative 1/2. So add them all together. What does that give us? 0. Okay, it's 0. So 0 makes perfect sense because when you have a conservative field and when you're moving around a circle, what happens? How much total work did you do? 0, right? Yeah. So essentially, if there is a closed loop or closed curve C and its vector field is conservative, you don't need to do anything, right? All you need to do is just write a 0, right? So now let's do a little summary of it here, okay? So those are important properties that we need to bear in mind here. Okay. And many of these, some of the properties we'll revisit when we go into the last few lectures, okay? So number 1, so I have basically the summary is that we have, okay, we have 4 equivalent statements, or you can call that property or theory, it doesn't matter, okay? So 4 equivalent statements, which means any one of them that I'm listed here is equivalent to the other one. So when you say one, that basically implicating the other 3, right? Yeah. So the first one is this vector field is conservative. Okay. So when you see the vector field is conservative, so essentially, which means the line integral over a closed curve C equal to 0. Okay? Yeah. For any closed curve C. Okay? Yeah. And second of all, this f, equal to this is a gradient field. Okay, it's a gradient field. Equivalency, what does it mean? It basically means if you see, oh, this f comes from here, so that means number 1 will naturally apply. Okay, yeah. Okay. And the third one is if the C is not a closed loop, C is not a closed loop, then that's the conclusion we see that is from the fundamental theorem of calculus for line integral, and this is basically so-called path independence. Okay, path independent. Okay. So this concept is commonly seen in many areas. Even in thermodynamics, I think you learn there is a path independent. Right? Yeah. So number 4, is this. Number 4 is actually from this number 2. Okay, and more or less is from number 2 here. So you have this this property here. So you see this f dot dr, right? This f dot dr, I think we derived a formula. Let's go back here to the beginning of the lecture. So this f dot dr equal to what? Equal to this, right? Equal to this. Okay, that's what we derive here. Okay, so let me write it down here. So this m dx plus n dy plus p dz, right? This is f dot dr. Okay. At the same time, we have this property, this second statement here, second statement. So what is the second statement? Second statement says this vector field comes from the gradient vector, this. So basically, m n p equal to what? Fx, Fy, and Fz. That's the second statement, right? So in other words, this m equal to partial f over partial x, and n equal to partial f over partial y, and p equal to partial f over partial z. So this expression can be replaced with fx dx, and fy dy, and fz and dz. Okay. Yeah. Okay. Yeah. So that's the four different statements that you're gonna you should remember. They're all talking about the same thing basically. Okay. They're all talking the same thing. It's one special case, conservative field, or f comes from del f. Okay, the vector field comes to del f. Okay. Any questions? All good? Yeah. So now let's solve let's solve two questions here. So the first question is, how do I know that this vector field f is a conservative field? So basically, how do we check if this f is conservative? Okay. How do we check this one here? So given a vector field f, how do we know that? So here's another theorem, okay, another theorem that we can make use of to check if this f is a conservative or not. So this theorem says this. So a field f is conservative if and only if, okay, so if and only if del cross f equal to 0. Okay, so del cross f equal to 0. So that's a theorem. And I'll provide you a short proof of it here shortly, okay? But or maybe just a description of proof here. But the proof is not important. It's more of applying this thing here, okay? Yeah. But first of all, let's see what is a del cross f in terms of the operation. How do I calculate this del cross f first, right? Yeah. So del cross f, it's a cross product. So cross product I, J, K. Okay. What is the del here? Del is an operator, right? What is del here? Del is an operator. Remember in the beginning of the first lecture, actually, you already, I actually talked about it in 246. When we learn many so-called linear operators. What is a linear operator? Because if the operators satisfy what? The superposition, right? So there are different linear operators. This d over dt, that's a linear operator. This del, this is another linear operator. Okay? Yeah. And this del cross is another linear operator. As next we're going to learn is del dot. That's another linear operator. Okay? Yeah. So your journey of a calculus basically will end up at these couple of things that are here. Yeah. So the second row is the del, which is what? This. And the third row is the vector function f. So m, n, p. Okay? So this is a del cross f. Okay? This is del cross f. So that's a cross product. You treat the three things as if they are a certain kind of quantity, right? By calculating the determinant of the 3×3 matrix. So all you need to do is calculate the determinant, and you actually will end up with this. So as you probably noticed, I posted the formula sheet for final exam, and this is on that formula sheet, okay? Yeah. So that's the result of this cross product. Now the theorem says a vector field is conservative if and only if this cross product is 0. Then what does it mean by this cross product is 0? So if this is a 0, basically means what? The 3 components here are 0. Okay? So that essentially give you 3 expressions. One is partial p over this equal to this, and the other is this. Okay? Yeah. This is what this theorem basically implicating at here. Okay? Yeah. Is that good? So let's revisit this language here. A field this is conservative if and only if this. Now, basically, in terms of mathematically, what this means is when you're trying to prove this theorem, you need to prove 2 things or 2 parts. So logically speaking, so the part 1, what you need to prove is, the part 1 is this: if f equal this, if f equal this, we need to show, let's call this is equation number 1, let's call this is equation number 1 here. So we need to show equation number 1, holds. So basically, see the idea is, if f is conservative, then we need to show that this is 0. If this is a 0, then we need to show that f is conservative. If we can prove these 2 logics basically back and forth, right? Then we prove this theorem. That make sense? Okay? Yeah. So I'm not going to go prove this one here, but basically that's the idea. Okay? So the part 2 is if the del cross f equal to 0, if this cross 0, we need to show that this f is conservative. So the second part is when if I want to show, the first part is actually pretty easy. You can check out my lecture notes. It's very easy to prove. The second part, we can't prove it right now. The second part of the proof needs a theorem called Stokes Theorem, and that's what we're going to cover in the last lecture or in the last week. Yeah. So when you're saying show that this is conservative, I can equivalently say what? I can equivalently show that this f dot dr and then what? C equal to 0. Yeah. So that's actually where the Stokes theorem will come into picture. It's using a surface integral called flux. So that's basically where the second part will be proved here. But if you're interested, if you're keen, basically that's how you should prove this this theorem. But in terms of the application, it's pretty simple. So you already, the first question that will ask you is, here's a vector field f. Please show that this vector field f is conservative. So how do I do that? I will just do the cross product of this guy here and get this. Or in other words, all you need to do is calculate 1, 2, 3, 4, 5, 6 partial derivatives and do this comparison using the formula sheets. You see what I'm saying, right? And if they're all the same, basically these two the pair same, these two the pair same, these two the pair same, then what's your conclusion? F is conservative. Yeah. So it's pretty straightforward. There's really no trick here. Just apply the operations, you'll be fine. As a matter of fact, often in time, what we're dealing is probably is not a 3D field, it's a 2D field. So in other words, if this vector field is only a function of x and y. Okay? Yeah. So basically, which means there is no p component. There are only this m and n component. So there is no z component either, right? That's planar field. Okay, that's planar field. And if this is the case, then what would that what does that mean to this formula now? So there's no p. Basically, the del cross f, what would be the result? There's no p and there's no z. There's no p here, so this is 0. There's no z here, so that's 0. No z, 0. No p, 0. So all you have is just the last one here. That makes sense, right? So it's a planar case. You only need to show is this equal to this. That's conservative field. Okay? Make sense? Yeah. So let's do a quick check here. Here's my vector field, right? Here's my vector field. Can you check whether it's a vector conservative or not using this theorem? And what's the m component? This is m. What's the n? This is n here, right? So m equal to y, and n equal to x. Then if I need to apply the formula, I need to verify partial n over x equal partial m over y. N equal to x, m equal to y. And guess what? 1 equal to 1. There we go, right? That's a conservative field. Okay? Yeah. Okay, so having said this now, your focus, of course, is basically don't be fooled by the long expression of this vector field, right? You need to stick to the formula, okay, when you do the verification. So I'll probably write it here. Then f is conservative if partial n over partial x equal to partial n over partial y. Okay? Okay, so that solved the question, how do we know whether a vector field is a conservative field or not? Okay, and the last question is, if f is a conservative field, okay, if f is a conservative field, as we learned from those 4 properties, this 1, 2, 3, 4 here, if f is a conservative, which means what? F has to be somehow from a scalar function f, small f. Does that make sense? Yeah? So if f is a conservative, then you will be able to generate this vector field f by doing this gradient operation on a scalar function f. So the question is, how do I find that small function f or scalar function f at here? Right? Yeah. So f is conservative, then f equal to del f, right? So basically, how to find this f? Okay, how to find this f? So that the gradient of this f equals the vector field, capital F. Okay? Okay, so I'm going to use an example to show you how to get this. Okay, this is basically basics of integrals here. So let's take an example. So f equal to this. So here's my f, okay, vector field f. So in other words, the m function, this is a planar case, so m equal to 6xy squared cubed, and n equal to this. Okay? Yeah, so m, n equal to this. So first step, I want you to verify whether f is a conservative or not. So we're a bit of running out of time, but you can easily verify. You can see that basically partial n over partial x. You'll see that they are these two are the same thing. Okay, if these two are the same thing, so the vector field f is going to be conservative. All right? Yeah. Well, there's no trick here. Let's just do partial derivative, and you see that. Okay. So f is conservative. So if f is a conservative, then what kind of a scalar function? Okay, there's no z, so just xy. So what kind of scalar function that can generate this vector field f? Right? That's the next logic question right here as we ask. Okay? So here's what you do now. We need to find this scalar function f. And based on this relationship, so we know that this gradient f equal to f. So gradient f equal to f meaning what? Meaning partial f over partial x, partial f over partial y equal mn. Okay, does that make sense? Yeah. This vector equal to this vector. So that means this partial f over partial x has to be the same as this m. And the partial f over partial y has to be the same as the n. This is m, this is n. So mn, you know it already. You just don't know what the small f is. Okay? But you know, now you know the two partial derivative. Okay? One is equal to m, one is equal to n. So then the next step what you do is, then you got to start make use of these two relationships to get this scalar function f. So what we do is we start from one of them. You can start from either of them. So let's start. So start from this relationship. Okay, start from here. Starting from here, when you do partial f over partial x, what happened to the y? You consider constant, right? So now consider y as a constant. Now I'm going to basically integrate both sides. So we're going to integrate both sides here. Okay? But this is not a very formal integration. So what we're going to integrate is this. So let's integrate. So move that partial x to the other side. Right? You're integrating now with respect to x. Okay? Integrate with respect to x. Because you're considering the y at this stage as a constant. Okay? As a constant. So the integration of this left side is essentially the function f. Okay? Essentially the scalar function f. The integration on the other side is integrating the m function. The m is 6xy squared minus y cubed, and then dx. Okay, dx. Okay, so give me a couple minutes, we'll be able to finish this. Okay, yeah. So usually the integration nothing new. So you're integrating this guy. When you're integrating with respect to x, you're considering the y as a constant. So what will be the integral? What will be the antiderivative for this one here? Exactly. Well, typically you would plus what? Plus a c. But that's only when you have a scalar function, single variable. So you put a constant c there. But right now, we're just not dealing with a constant. There's another one, y. Y is also considered as a constant. So you need to plug a constant, but this is a function of y. Can you see the reason? Because why? This is, what do we call this side here? Antiderivative, right? So the derivative of this with respect to x should give me back which one? This one. So the derivative of this with respect to x, because this is a function of y, so it basically is a 0, right? So that's why you don't put a constant c at here. You put a constant, not a constant, you put a function of y at here. Is that clear? That's often the very common mistakes you would make if this is the case here. So this is what you get after applying the first condition. All right. Then we have another condition, this one. Okay, this one here. We have to make use of the second condition here. Second condition is this. See, from the first step, you got f equal to this. Now I'm going to apply this one over here. I'm going to basically take partial this whole chunk. Okay, I'm going to apply the partial of this with respect to y, and I'm supposed to get what? N. I'm supposed to get n, and n is known, and that's 6x squared y minus 3xy squared. Okay? Yeah. So what's the partial derivative of this side here? You get 6x squared y minus 3xy squared plus the derivative of this with respect to y. It's not a partial derivative. It's actually just what? Derivative, right? And that's the other side is n. So you compare two sides here. What do we say? That means this r prime y equal to 0. If r prime y equal to 0, so that means the r of y equal to constant c, any constant c, right? Yeah. Then what is the scalar function f? It's this plus a c. That's it. Okay, for this question. See the procedure, right? That's basically how you end up with this potential function, small scalar function f. Sorry, it relates here. Any questions? All good? Yeah, come here to us. Yeah.